All right, let's talk about graphing a logarithmic function. How does this work? So graph y equals log base 3 of x. To start this, we're just going to go the old-fashioned route of plugging in x's and y's and making a table. Now, I'm going to make a suggestion that's a little bit different here. If you're going to do this, what I would do is I would change this to its exponential form, 3 raised to the y equals x, and I would then, and this is different, I would pick y's instead of x's. Okay? And you're going to be just fine if you do that. If you're graphing this by making a table, transform it into this form, and pick y's instead of x's. It just makes it easier. So in other words, I can pick y's to be my kind of my standard things. Um, 3, 2, 1, 0, -1, -2, -3. If I pick my x's, I can do that, but I have to pick special x's, just x's that are powers of 3. But if I'm picking y's, I'm allowed to pick anything I want, and I'm plugging them in over here for y. All right, I'm plugging them in over here for y. All right, so I'm going to plug 3 in. 3 to the third is 27. Easy as that. So x is 27 if y is 3. 3 to the second is 9. 3 to the 1 is 3. 3 to the 0 is 1. 3 to the -1 is 1/3. 3 to the -2 is 1/9. And 3 to the -3 is 1/27. And so when I go to graph these things, now I just plot them. 27 and 3, well, we'll just say that's way out here. 1, 2, 3, not to scale clearly, but there's 27 and 3. We'll put 9 and 2 about right there. And now we can do 1, 2, 3. We'll be a little more careful. 3 and 1, 1 and 0, 1/3 and -1, 1/9 and -2, and 1/27 and -3. So our graph is going to look like this. And that's the graph of log base 3 of x. Well, it turns out that there's some key features of that graph we want to focus on. Number one, notice it doesn't live over here. None of the graph doesn't exist over here. The graph never is never defined for any x value from 0 into the negatives. In other words, its domain, it has to be positive. The graph goes through 1, 0. That's going to be true of every logarithm, no matter what the base is. We did base 3 here, but if it was base 4 or base 5, it would go through 1, 0. This side climbs, and it keeps going. It'll eventually go to infinity, but it goes slowly. Okay? This side becomes asymptotic to the y-axis, and it goes to negative infinity. The other thing is this graph goes through 3, 1. So those 2 points right there and there kind of form our anchor points, 1, 0 and 3, 1. So the reason I say that is because if, for instance, you want to graph one of these that is with a different base, log base 5 of x, for instance, I know this. Remembering those properties I talked about, it's going to go through 1, 0, and it's going to go through 5, 1. Those two form the anchors, and then it's asymptotic going to negative infinity, and there's your graph. So that's what those graphs look like. So now you have this new family of graphs that you can add to your basic graph collection. This allows us now to shift and translate these graphs as well. So if we needed to say graph y equals log base 2 of x plus 3, okay, we'll put parentheses around there. We know that we're going to take the log base 2 of x graph and shift it up 3. So the log base 2 of x graph is going to go through 1, 0 and 2, 1. There's log base 2 of x. I need to move it up 3. So this point goes up 1, 2, 3. This point goes up 1, 2, 3. And it's a vertical shift just up. So I can shift it up and down. This graph would be y equals log base 2 of x plus 5 would be the log base 2 graph here. This red one shifted left 5. So it moved left 5. In particular, this asymptote would also move left since it's a vertical asymptote. So we can shift and translate these graphs and their functions just like we could with all of our basic functions.